The first topic in chapter 4 deals with Newton's second law, which in turn deals with forces. Forces are pushes or pulls, one or the other. The units of forces, the unit of a force is the Newton, after Isaac Newton. Before we get into Newton's second law, I want to describe an important property of vectors. Vectors in general, not just force vectors, could be displacement vectors or velocity vectors. If one vector is equal to another vector, then they're of the same length, have the same magnitude, and they point in the same direction. You could put one on top of the other, and the other couldn't be seen. So if a vector A equals a vector B, then the horizontal part, the x part of that vector, of the one vector, equals the x component of the other vector. And the same is true for the y components. Or we'll put that simple property of vectors to use later, not right away. We will be dealing with forces acting on a particular object, and it will have a certain mass. The mass of an object is a number, and it's a measure of how much matter is there. All right, so we commonly symbolize the mass of an object as m, and its units are kilograms. A kilogram is 1,000 grams. It takes 3 grams, for example, to make a penny. A dollar bill or a $100 bill weighs almost exactly 1 gram for what that's worth to you. Well, let the vector F be equal to the sum of the forces acting on an object, and I've already indicated, well, I'll indicate now that forces are measured in units of newtons after Isaac Newton, and we abbreviate the word Newton as N. Now we come to Newton's second law. Newton's second law says that the total force, sum of forces acting on an object, equals the mass of the object times the acceleration that is caused by those forces. An alternative form of F equals ma is shown here. Just divide both sides of the equation by m and reverse the order. Now we'll put to use the property I discussed earlier. We see that the vector A equals the vector F divided by that number, m. That means that the x component of A equals the x component of F, scaled or divided by that same number, m. And the same equation, or similar equation, is for A sub y. It's F sub y over m. Let's work a sample problem. We have an object of mass m equals 6 kilograms. Wherever it is now, imagine it's at the origin of our coordinate system, an xy coordinate system. At the moment we look at it, its x component of initial velocity is 2 meters per second. Y component of initial velocity is 0. There are 3 forces at this moment acting on this object and will continue to act on the object, pointing in the same directions with the same magnitudes. One force is a 100-Newton force directed along an angle of 30 degrees relative to the positive x-axis. Second force is 90 newtons, acting along a direction of 60 degrees below the positive x-axis. The third force, 120 newtons, making an angle of 70 degrees relative to the negative y-axis. Well, what we wish to do is to determine what the x and y coordinates of our particle will be 4 seconds from now. Well, the x coordinate of an object moving in a plane is given by this equation that you've seen many times before. V naught x times t plus 1f(a)x t squared. Can we find x right now? Well, no, because while we know the value of v naught x, 2 meters per second, and t has been specified as 4.0 seconds, a sub x is not given. So in order to find the x coordinate, which is half of our ultimate goal, we need to first determine a sub x, the x component of the acceleration of our object. The same story can be told about the y coordinate. In order to find it, we need to know v naught y, and we do, it's 0. T is specified as 4.0, but a sub y is not given. We're in the same boat as we were with a sub x. We need to calculate a sub y. Well, I'll put to use the two properties I described earlier about a vector that is equal to another vector. We have the vector A equals the vector F divided by M. So this statement is true, and so is that, and I repeat those two equations here. In order to find the a sub x and a sub y values, we need to know f sub x and f sub y. We already know m, it's 6. 6. Well, let's discuss, and I will not write down, the calculation of f sub x and then f sub y. I'll let you take a moment to look at it to see if you can determine for yourselves before I describe how to find those components. All right, did you figure it out? Let's do the sum of the 3x components. The x component of the sum of these three vectors is the sum of the 3x components. Exactly the same situation existed when we were adding displacements. The x component of the net displacement is the sum of the x components. The same story is told for the y components. All right, I'll point to the three vectors, the three forces, and say how we could write down the x component of each one. 100 cos 30. Plus 90 cos 60. Now, the 120 Newton vector points into that quadrant. The shadow of that arrow cast above it onto the negative side of the x-axis means that the x component of this vector is a negative number. Start with a negative sign. Here we go. The x component of this is negative 120 sine 70. But since that's 20, the complement, you could say the x component is negative 120 cosine of 20. Add those three and you'll get the final x component, which I determined was this number here, 18.84 newtons. Now let's talk about the three different y components that have to be added to get the total y component. 100 sine 30 minus 90 sine 60 minus 120 sine 20, or you could call it negative 120 cos 70. Final result for f sub y is shown here at negative 68.98. Well, now we can use these equations with these numbers to divide by m, which is 6 divided in both places by 6, and we get these values for a sub x. I won't finish the problem because it's straightforward enough. Now that we have the values of a sub x and a sub y, put them in these locations to get the final values we were looking for, which I won't report. The final values of the x and y coordinates of our particle.